Since this is perhaps our last opportunity to make a presentation at a SENSAM workshop, I want to make sure to thank our sponsors for this and the opportunity we've had to work on this project for the last 8.5, 9 years. And also like to acknowledge all the researchers on our team, past and present, and to say proudly that those who are in the past mode have all gotten good jobs, and those that are in the present mode seem to all have good job opportunities, which I'm happy for. So, as you all know, the reason that we're interested in this topic is that there is a lot of sediment being moved around the world in coastal waters. The price of sand has escalated significantly. It's a valuable resource, and if it's also not placed properly, it can become a contaminant. The turbidity and in some cases the associated chemicals that are associated with the sediment are contaminants. And so we're interested in the understanding of how sediment moves when it's intentionally placed in coastal waters. So I just sort of summarize what it is that we have done. I think we've done in the last 9 years or so. We've spent a lot of time looking at the fluid mechanics of the various flow structures that result when sediment is put into the water in continuous or instantaneous form above the water surface, below the water surface, etc. We, probably the best word is to say, rediscovered a flow structure that is quite important. That's what we'll refer to as the clump. We have taken this understanding, which mainly has to do with near-field fluid mechanics, and we've integrated that into a far-field three-dimensional circulation model to extend the length of our simulations from scales of the water depth to kilometers or so away. And we have put various models into an umbrella package, which we call BS DM, Barge Sediment Disposal Model, which we're now in our second version, and it's receiving some attention from users in the field. So let's start off with where we were, or where the state of the art was. It dates back to the late 1970s when Cohen Chang from Caltech and Tetra Tech developed a model to try to explain the behavior of sediment thermals or clouds when they were released instantaneously into the environment. And they had a simple, effective, but in many ways very simple model saying that this is a uniform structure that descends because of its negative buoyancy. They acknowledge that sometimes sediment that's released doesn't all get into this thermal, but they only had ad hoc ways to quantify that. And if you waited long enough, the sediment particles would eventually rain out of the thermal, which descends, it decelerates, and they had a fairly primitive way of acknowledging that. So we have tried to improve our understanding of these various parts of the plume and how they are affected by various conditions, including the ambient conditions, waves, currents, stratification, and turbulence. So Adrian Lai developed a model of the internal circulation. He borrowed from the Hills expanding spherical vortex model to describe what the flow circulation is that's inside and outside of these thermals. And the advantage of that is that he can use that to drive the circulation of the particles inside with a Lagrangian particle tracking model, and that allows the particles to rain out of the plume in a swarm that is continuous as opposed to instantaneous. It also allows for different size particles and the whatnot, so it gives a much better description of what's happening. And if this works, you can see a simulation of the measurements versus the simulation that does a pretty good job of reproducing the character of this phenomenon. And as I said, it also works for various sediment sizes, so you can have sequential settling of particles out of this plume. So one of the big issues is how much sediment does not make it into the plume. It's hung up in the so-called trailing stem. There was some research done by a previous student, Gordon Rugaber, who was from our group but was not part of this project, and then Jim Gensheimer, who was part of this project. And so Adrian, again, has tried to summarize this information. This is the fraction of the released sediment that is found in the trailing stem, and that is vulnerable to being dispersed in the environment when there's waves, currents, turbulence. And that increases. This is 5% all the way up to 100%. These are different release conditions. This is a normalized ambient current, and going in this direction is the normalized settling velocities of the particles. So as you get the smaller particles or faster ambient currents, you tend to get more mass in the sediment, in the trailing stem, and hence more vulnerability to pollution associated with the dredging or land reclamation events. And they're somewhat different, but the same trends for different types of release conditions. We also had a theoretical basis for this. We did a lot of numerical modeling, and this is the only aspect of that I will talk about. But Rochen Wang looked at the development of starting plumes and vortices through large eddy simulation, and he built upon earlier work by Garab et al., who identified the behavior of the sediment thermal, or in his case, a vortex, and how it relates to the amount of fluid that is introduced into the environment. In this case, he was using a piston to try to generate a vortex. And it turns out if the stroke length divided by the diameter is larger than a certain value, that certain value is around 4 for neutral buoyancy, all the material does not make it into this recirculating vortex structure. If it's less than that, it does. And one of the things Rochen did was to look at what happens when you add buoyancy. So this is, instead of just a jet, it's a buoyant jet, and the buoyancy is increasing to the right, and this critical value of L over D goes from about 4 up to maybe double that. And that at least gives some insight as to the duration of a discharge, over which time all of the material will be assembled within the parent thermal. So as I said, we looked at the behavior of these thermals under a variety of environmental conditions. And I guess the simple motivation was to see if we turn up these environmental conditions, can we reach a point where this thermal stops becoming a thermal? Can we break it up? And so we first of all tried to do this with waves. And it was a nice study, but as far as we could determine within the limits of our laboratory experiments, which scaled up to field waves of about 2 meters and 9 seconds, we couldn't get the waves to destroy these thermals. They would descend, they would follow the orbital velocities with just a slight lag due to their inertia, but they would basically end in the same spot that you would be able to predict. So waves did not appear to be a problem, at least within the typical environmental conditions you would find in coastal regions. Not the same story with currents. Jim Gensheimer looked at the behavior of thermals in sediment thermals in currents. This again is a normalized ambient current speed. This is a normalized but differently normalized particle size. So this gets to be small particles, this gets to be high ambient currents, and that combination moves one from what he defined as weak currents to strong currents being strong enough to blow apart the structure of the thermal. And so basically this was parameterized into an equation, and if you apply that to the field, you can identify the conditions where it would be safe to release sediments and those where it would not be. And in this particular example, if you took a cubic meter, which is typical of a dredge bucket, of fine-grained sand. This transition halfway in between this strong and the weak was about 0.6 meters per second. So if you have tidally reversing currents, there would be a window of time when it would be acceptable to release and a window of time around the max flood, max ebb, that it might not be. So as part of this project, we built a large tank. You've probably seen it on the first floor of the laboratory building. We call it the Houdini tank, or sometimes the Houdini tank number 2, since we have one at MIT. And one of its claims to fame is it's got a pulsating jet array that produces turbulence, shown schematically here. These are simple bilge pumps that are programmed to come on and off at random intervals and produce homogeneous turbulence. And we've done a lot of studies as to just how clean that turbulence is. And Adrian Lai has done a lot of work characterizing the effects of turbulence on plumes. One of the key simple features is just to ask how much turbulence, in analogy with how large of the waves or how strong a current, how much turbulence is necessary to have this plume break apart. And it turns out ultimately would break apart, but what is the depth? And it turns out that depends on a buoyancy flux, how much flow of how dense material is coming out. Beta is simply a spreading length. It's typically about 0.1, and epsilon is the rate of kinetic energy, turbulent kinetic energy dissipation. So it's an indication of the turbulence. The stronger the turbulence, the shorter this depth, the greater the buoyancy flux, the larger that depth. And we try to find out how this compares with what real conditions are. So for coastal sediment discharges, there really should be a range here, but these values, 1,000 meters, are way larger than typical water depths. So turbulence does not seem to be a problem as far as coastal sediment discharges is concerned. We looked at wastewater discharges, and they might be on the margin, but probably not. What we think is actually an interesting area to explore would be indoor air quality and ventilation and convective plumes due to human activity. And so the typical depth lambda is around the ceiling height. So it's probably important in a case like that. And lastly, we've been looking at stratification. Cindy Wang has done some experiments at MIT. She's continuing those experiments here at CREATE. The experiments at MIT are in a towed stratification tank. And so she stratifies it and tows it. She's looking at the depth at which the plume intrudes into the ambient at a level of neutral buoyancy. That's a declining function of the current speed. She's also looking at the deposition. This is increasing particle size, and so the deposition patterns are becoming shorter and shorter with denser, larger particles. And the experiments and a model that she has show good agreement. So I want to talk about this new formation that we've identified or kind of rediscovered, and maybe we can get it back. Maybe we can't. Maybe we can. So on the left, we have a sediment thermal that's made up of relatively coarse material. On the right, we have a sediment thermal which is in all ways equal, except that it's finer grained material. It's finer grained, but it's not cohesive, so it's still non-cohesive. But you see dramatically different behavior. One of them is holding together as a sediment thermal. The other one is sort of falling apart as a clump, forming a wake. And so we've had a lot of fun trying to extend these observations into some theory. On the left, we see another way to represent this, but again, this is the descending thermal. This is the clump. And these are distinguished by a value of this cloud number that's about 0.03, probably only good to one of those significant figures. And we've argued, and I think prove theoretically that the behavior and the distinction of this behavior has to do whether or not flow can flow through this porous cylinder or porous sphere. If you have relatively coarse material, the porous cylinder or sphere can settle through the water, and the water will help create this thermal. If it is not the case, it'll go around it, and you'll get this clump formation. And this cloud number, again, is a settling velocity divided by a characteristic size of the thermal. So larger thermal radius or smaller settling velocity tends to promote this clump-like behavior. And the interesting aspect of this, perhaps somewhat problematic, is that if you take a given grain size and you go from the lab, where you might typically be in a cloud formation, you take that same sediment size and go to larger volumes, as in the field, you're attempted to get into the clump formation, which means it may be harder to find thermals in the real world. So we've taken this information, we've put it into far field models. In general, we could use any number of available three-dimensional models. We've been using EPA's model, EFDC, and basically we've represented the loss through the trailing stem and also the swarm formation and how that gets in the environment. We've included algorithms for sorption, desorption, even stratification and whatnot. And we have we have a little video, but I'm not able to get that at this point. We'll look at the last thing, which has to do with gravity currents. And these are important. Once the sediment reaches the bottom, it starts to spread. And we've developed a better model, a box model, to look at these gravity currents that are neither circular nor two-dimensional, which are the two endpoints that people have used. But Genway Air has developed such a model, and experiments and observations of deposition patterns agree quite well. So we've taken all these models and we have put them into a umbrella model, which, as I said, was called the Barged Sediment Disposal Model, BSDM. So we have a classification scheme that, depending on characteristic length scales in the environment or of the discharge, one can categorize the plume behavior as one of about 8 different categories. This is patterned after sort of a similar structure that is used for sewage plumes, desalination plumes, and whatnot, called Cormix, and this is our version of that here. And so we have little modules for each of these, and they're packaged together. We've put them into a model. We are offering this free of charge. You can take a look at a little more information about this in the website here. And we've had interest from a number of organizations, principally the companies that are involved with dredging operations, dredging and land reclamations in Singapore that are required to comply with regulations. And that's it. Thank you very much.